Hello, I think two peoples will get removed and they have to admit again. Sudatna and I think because I started the recording of the meeting because it will help me to upload on LMS because this is a procedure. Okay, I think Sudatta, two students have to join again. Okay, I will admit them. No problem. Okay, now see, here there are three experiments: inverter, NAND, NOR, and half adder. Okay, this is experiment number one has these many parts, and experiment number two is 2 as to 1 marks using logic gates. I told you logic gates. You remember 20 transistor, or you can implement by using static CMOS 12 transistor and a transmission gate. Okay, and a single bit SRAM cell. These three experiments are over there, and the experiment number one has four parts. You may say inverter, NAND, NOR, and half adder. Okay, now whenever you are starting with the microwind, first the design must be ready with you. Means if you talk about an inverter, you must know how the transistor, that is a PMOS and NMOS, are connected in the inverter circuit. If you are drawing the layout of NAND gate, then you must know that how this NAND gate is being connected, or the transistors in the NAND gates are being connected. You must know the circuit, or another way you can say that you must go for the design, and design should be ready with you. Then you can go for a microwind. Okay, now I want to show you now how to start the microwind. To start the microwind, actually you can have your own student version, or you can have any other version. I have microwind 3.1 full, which is on my C drive. I will double click on this. I will double click on the system folder, and inside the system folder you will find microwind 3.1 exe. You just double click on this. Okay, you just double click on this, a new window will open. A new window will open. Okay, and this will be the screen for your microwind version 3.1. Okay, now whenever you are going to see, you will see a black screen in front of you with the dot or a mesh like structure of dots. Okay, now whatever the black thing you are going to see in front of you is nothing but a P substrate. What it is? It is a P substrate, because now you just think that you are drawing a layout of an IC. If you are drawing a layout of an IC, then what are the things essential? You need a substrate, you need a P plus diffusion, you need a N plus diffusion, you need a polysilicon, you need different metals to have a connections. Okay, so all these things will be available in this particular software. That's why first thing what I want to show you, that whatever the black screen you are going to see in front of you is nothing but a P substrate. On this P substrate, suppose that if I put a N plus diffusion, because you know that if I go for a N plus diffusion on P substrate, then I am able to fabricate a NMOS. I'm able to fabricate a NMOS. Right? Now see, I put a N plus diffusion. Here you can see on the right hand side, the name is given to this as a palette. Okay, this is called as a palette, where whatever the thing being required to draw the layout of any IC is being shown over here. And this palette contain NVL, then N plus diffusion, P plus diffusion, then contact, then metal 1, metal 2, like these things are being shown in the palette. Okay, in the palette these different things, plus different types of contacts are also available in the palette. Then a ready-made MOS generator is over there, then a capacitor, virtual capacitor, then virtual resistance, virtual inductor, then VDD supply, then high voltage supply, ground, then whatever the input you want to apply, that input is also being present, and whatever the you want to observe, that is a visible node, is also available on this palette. Means this palette is the thing, whatever the thing you want to do, it give a shortcut path for you. Okay, and from this palette I have taken a N plus diffusion and placed over here. And if on this N plus diffusion, if I put a polysilicon, now see, on the N plus diffusion, I put a polysilicon, and now I'm saying that this is a transistor. It's very difficult to believe. It is very difficult to believe. But how? Because once you understand this software, you will come to know that what is happening. For understanding purpose, I will put a what you can say N plus diffusion again to this side. Now see what I will do. I will take a cross section. I will take a cross section. This is actually whatever you are going to see. This particular thing is a top view of your layout. This is a top view of your layout. Means if you want to see what is the, if you want to take a cut section, and if you want to see the depth, what is happening in the depth, then I put over here is a, you may say, a N plus diffusion. And if I take a 2D cross section, this is a vertical 2D cross section. I clicked on this and I have taken a 2D cross section for this much portion only. Now you can see that what happens. Actually, it is showing the next part also. Okay, I don't want to see this particular part. If you see this particular cross section for this much part, in this much part, you will directly see the N plus diffusion, and whatever this gray color is over there, this gray color is a P substrate, and above this, these are nothing but the different layers which are available. Okay, and here actually means violet color. A violet color, I don't know is it visible to you or not. A violet color thin layer is you are going to see. That thin layer means between this yellow part and this white part, there is a thin layer of SiO2, and above that SiO2, this is different thing. Okay, now what the thing is happening for whole part, जितने पार्ट के लिए मैंने क्रॉस सेक्शन लिया था, पूरे पार्ट में आपको क्या दिख रहा है? Okay, I will show you in different way. Just a minute. See now. I will delete it and I will show. This is a delete button. This is a delete button. Okay. Now I will show you again. Again, I'm going to take a 2D cross section, and now you see. See now, for whole part, the N plus diffusion is available. Now what I will do, I will put a polysilicon over there. Polysilicon is nothing but a gate. Polysilicon is a gate. Okay, and I will take the 2D cross section. See now, I'm taking a 2D cross section again. Now, how this structure is? It is exactly same as the structure of your transistor. Whatever this is, what? This is a P substrate. On this P substrate, there are two heavily doped N regions. And you can see that earlier, this was a full N plus region. But as soon as I put the polysilicon over there, what the thing happened? Whatever the N plus was over there below polysilicon, now it is absent. It is taken in the process itself. No need to remove that polysilicon. Means if anybody says that, I will prepare a transistor like this. That is, this is a N plus diffusion. Okay, this is a N plus diffusion. And between this, I will put a polysilicon. This is a wrong process of a what you can say a transistor. Okay, whenever you want to prepare a transistor, you must prepare by putting a single whole layer of, you can say, a N plus diffusion, and above that N plus diffusion, you can put the polysilicon. Okay, will become a transistor. Now this transistor does not have any connections. This transistor is being prepared, but transistor does not have any connection. To make a connection to this transistor, how to make a connection of this transistor? With the help of metals. I will show you that one with the example of a inverter. Now, just I will delete all this. See, I have deleted this. Now, whatever the menu which are available over here, as this is what you can say a simple okay, as the menus are similar to our Windows system, like that. This is open, this is save, this is a drawbox, this is a delete, then this is a copy element, this is move, stretch and move, this is a zoom in, zoom out, show all, this is electrical nodes, then this is a run the circuit. Okay, then this is a measure distance. This is 2D cross section, 3D cross section, the process step in 3D, then design rule check. This is the add text like that. This is a palette. Okay, show palette. See, by mistake, if you means if you closes this, you just click on this, your palette will be available. Okay, and this is a navigation case. Okay, now what I want to say that if you remember our inverter circuit, the transistor means there is one PMOS and one NMOS, right? There is one PMOS and one NMOS. And another thing is that these are connected. How they are connected, you know, that one terminal of PMOS is connected to VDD, one terminal of NMOS is connected to the ground, and one terminal of PMOS and NMOS are being connected, and it has an output, and gate of both are shorted, and it is an input. This is a very simple diagram of a CMOS inverter. Now I will draw the layout for CMOS inverter. Now see what I will do. I have to draw the P transistor. If I want to draw the P transistor, which type of substrate is needed? You have to unmute your mic and speak. If I want to go for PMOS, which substrate is needed? N substrate is needed. And what I told you that this is a black is what? It is a P substrate. Then quite obvious, it is not possible for me to fabricate a PMOS on this. If I want to fabricate, first I have to make an N substrate. And if you want to make an N substrate in microwave, there is an option that is an N well. And this is the N well which I put over here. And once I put this N well, now whatever the rest thing is over there, this rest thing is a P substrate, and this N well will act as a N substrate for a PMOS. And inside this, I can put a P plus diffusion. Inside this, I can put a P plus diffusion. Once I put this diffusion, I have different options that I can enlarge, then make a size lower or small, depending upon this. This is a stretch and move command. I will click over here and I can reduce the size. I can click over here, I can reduce the size. I can click over here, I can reduce the size. Okay, this is just I'm showing you. Okay, and is it correct? Okay or not? I will go for DRC. Click on DRC. If by mistake, if I put the anvil too much nearer to the means you can say substrate, and if I click on the DRC, it will show an error. What it is saying that diffusion is too much nearer to the wall. Okay, extra anvil surrounding is should be less than it is a less than 6 lambda. It must be greater than 6 lambda. So I will make it larger, and I will put okay, I will just minus the okay now, and if again I will click on DRC, it will give me no error. Okay, now what the thing, similarly I have to go for a N diffusion for fabricating a N transistor. Then I'm going to put a N transistor or N plus diffusion over here like this. Okay, now I will put a polysilicon common on both, because gate is common for both, and it is a CMOS. Okay, I can adjust the size of gate by changing this. Okay, here I put a gate, means this gate is already shorted. Gate is already started because this is a gate of PMOS as well as gate of NMOS, and this is already started, means here I can apply my input. Okay, now what one terminal of PMOS is connected to VDD, means I need a metal, and this is a one terminal of PMOS connected to VDD. Okay, this is a metal, and this is to be connected to VDD. I will take from over here a VDD supply and I will put over here. Now one terminal of PMOS is being connected to VDD. Then one terminal of NMOS is connected to ground. This is a one terminal of NMOS, and which will be connected to the ground. This is a, I'm going to connect it to the ground. Okay, now what I want one terminal of PMOS and one terminal of NMOS is to be connected. I will go over here and I will connect it. Okay, and I will just check DRC error. Is there any? No, there is no DRC error. Okay, now what I will do, if you see that, if you want to see that this is not connected, what I want, this metal must be connected to the P plus diffusion. This metal must be connected to the N plus diffusion. That's why I will check. I will show you that it is not connected. See, by mistake it is clicked. Okay, see now. I will go for a cross section. Is there any connection between this N plus substrate and sorry P plus substrate and the metal? No, these are not connected. Okay, yes, metal is present, but it is not connected to the P plus diffusion. That's why what I have to do, I have to connect the N plus and metal one. Here you can see that contact metal and poly. This is a contact N plus diffusion. See, this is a contact P plus diffusion and metal one. I will click on this and I will put a contact like this. Okay, or another option is click over here, right click on this and say connect layers. Will do. Okay, and now I will show you the cross section, 2D cross section, and now you check it that how it look like. Now you see the cross section. Now can you see that the metal one and P plus diffusion is connected? Okay, similarly same thing I must do in case of what, the N transistor also. So I will instead of going over there, I will directly say right click and connect layers. Or what I can do, that I can go to the N plus diffusion and metal one and I will put it over here also. Like this also I can do. Okay, now my circuit is ready. My circuit is ready. And where from I have to take the output? For output, I am going to take from these two shorted points. I'm going to take the output, and output is a visible node and its name is Y. Its name is Y, because I'm saying that Y is an output. Okay, I'll say assign. Clear now? Now yet I have not applied the input. My circuit is ready. Okay, my circuit is ready. I will check the DRC. I will check the DRC. Okay, there is no DRC error. There is no DRC error. Now what I will do, I will apply the input. See now, to apply the input is nothing but a clock. So I will say add a clock, click on add a clock and put it over here and give the name as A. Give the name as A. And it is asking me what is the low time, what is the high time, like that. So I will keep it, let us say 390 means total time period. I will take 390 or 400 nanoseconds. Okay, and I will say assign. Okay, and now just I have to click on run to get the output. Just if I click on the run, it will show me the output. Oh, just a minute. Now it is showing an error. It is saying that the NVL is floating. You know that in PMOS, the substrate is connected to, in PMOS, the substrate is connected to VDD. That connection is remaining, and I have connected now substrate to VDD. Earlier, I have forgotten to connect it, but now I connected the substrate to VDD, and now I will click on run, and you can see I got the output. Okay, when I apply 1, the output is 0. When I apply 0, the output is 1. And what is the rise time? Rise time is 8 picosecond. And what is the fall time? Fall time is also 8 picosecond. Now what I will do, I will apply a capacitive load. Okay, now palette is not visible. Click over here, your palette is visible. Go to the capacitor and add a virtual capacitor. And I'm just, I will keep the same value, no problem. Okay, I'll keep the same value and I will say okay. Okay, I added 0.01 picofarad capacitor and again I'm going to run it. Now see what the thing happened. Now the rise time is 103 picosecond and fall time is 115 picosecond. Okay, now what I will reduce the value of capacitor so that you will see the waveform somewhat observable. Okay, and I will again run it. Now you can see that the rise time is 18 picosecond and fall time is 19 picosecond. Okay, now you have to understand that on what factors this rise time and fall time are dependent. Now I will show you. See that rise time means what? You are making it from 0 to 1. 0 to 1 means what? Who is responsible from 0 to 1? The responsible is a PMOS. Okay. Another thing is that if I actually what happened, I kept the length of the channel much more. If I reduce the length of the channel, it will be drastically reduced. The times will reduce drastically. Now I can show you. Now you can see. See now 13 picosecond and 12 picosecond. And now I can show you by capacitor also. I can go for earlier value of capacitor. I will delete the capacitor. I will apply again. That's the places with Y. It's conflicting with Y. Go to the palette. I will take the capacitor and I will put it over here. And now the value I will keep same. And I will run it. See now. Now it is a 61 picosecond and 68 picosecond. Now I want to show you that if I want to reduce this 61 picosecond, what I should do? Okay, either I should reduce the length L. Either I should reduce the length L. And another thing is that I should increase the width W. See now, I'm increasing the width of. Okay, the distance between the both diffusions is L. This is the length. I reduced the length and I increased the width. Now definitely what should happen? The conductivity will increase. The conductivity will increase and your rise time will be less as compared to earlier. See, earlier it was 61 picosecond. Now it is 33 picosecond. Now you can see that it is a 50 picosecond. Fall time is how much? 50 picosecond. If I want to reduce it, what I should do? I should increase the width of the N plus diffusion. See now, I'm going to run it. Now you can see that it is a 33 picosecond, which was earlier 50 picosecond, which was over there. Okay, this is the effect of width and length, as well as there will be the effect of a capacitor also. Okay, capacitor also, and this is a very simple way. Now I want to tell you that how much means you can say how much area is being required to build this my inverter. Okay, for that I have a one means you can say measure distance, and I have prepared the layout in this much region. I have prepared a layout in this much region. That's why I will tell you that how much is the means area I needed to draw this layout. I need the 2.75 micrometer to just a minute to 3.1 micro. Okay, this much is my the length and width of my you can say layout. Means you can see that whatever this length and widths are nothing but a micron, and here you can see that 0.2 250 micrometer is nothing but a 5 lambda. That's why what is my 1 lambda? My 1 lambda is 50 nanometer. My 1 lambda is 50 nanometer. It is an approximation nearer to the, you may say 45 nanometer, because my technology is 90 nanometer, because they told you to be in the specific technology. उन्होंने क्या बोला था कि you have to simulate it in the specific technology. You can see the bottom. At the bottom, it is a CMOS 90 nanometer 6 metal copper. Okay, strained SIGE. This is your, and its voltage is 1.2 volt. When I run it, you will see that because for 90 nanometer technology, your VDD is a 1.2 volt. This is a 1.2 volt VDD when I run it. That is the reason, because for 90 nanometer, this is the voltage specified, and you can see that the how much area is being required to draw my, means whatever the distance between these 2 points is nothing but a 5 lambda. ये दोनों पॉइंट में का डिस्टेंस कितना है 5 lambda, और वो कितना हो जाएगा फिर 250 micrometer. And how I come to know that? If I reduce the, what is the minimum gate length? The minimum gate length is 2 lambda. कितनी होती है 2 lambda, means your technology, and your technology is what? Your technology is 90 nanometer. If I reduce my length of the gate below 2 lambda, it will give an error. And what that error? The gate length must be 2 lambda. See now here, what it is giving an error. The poly width is less than 2 lambda. The poly width nothing but a gate length, and it is a 90 nanometer. In our case, it must be how much it is? It should be 90 nanometer. More than 90 nanometer. Actually, minimum is allowed is 90 nanometer. Okay. Hope that you have understood whatever the thing I taught. Once you understand this particular thing, you will understand the remaining layouts also. Okay. Now I will just stop the recording first.